Okay, so I'm going to talk to you about pressure effects on kinetics and how it's implemented in RMG, and mostly the same way it's done in RMG is how it's done in arcanes. I wouldn't guarantee 100% match, but pretty close. Okay, so there's a lot of different kinds of pressure effects on kinetics. Um, there's the obvious ones that you probably knew about from high school time, that when you change the pressure, you change concentrations. So for example, in piston, as you squeeze the piston, you change the concentrations. So you would expect that equilibrium would be affected, the rates of reactions would be affected. But there's another thing you want to know about is, do the equilibrium constants change? And it's helpful to look at the definitions. So the equilibrium constant is defined to be the exponential of the change in free energy of the reaction at the standard condition. So this thing does not have pressure in this expression at all because the G is evaluated at the standard condition, not at the actual experimental pressure. So this number definitely does not depend on the pressure. It does depend on the temperature really strongly. Now, because KQ is a constant independent of the pressure, then you can say, well, what's the expression for KQ? It's the product of the partial pressures of the products divided by the partial pressures of the reactants, all normalized to the standard pressure with the stoichiometric coefficients, just like as you learned in high school. And if you multiply this through, the ratio of the true pressure of the system compared to the standard pressure survives if delta nu is not equal to 0. So if you have a change in the number of moles of gas, then you have a pressure effect here, but the K doesn't have pressure dependence. So therefore this part has to also vary with the pressure in order to compensate. And so therefore you get expressions like this, that the ratio of the mole fractions to the powers is equal to the equilibrium constant times this correction that depends on the pressure. So the mole fractions definitely change. The equilibrium mole fractions definitely change with pressure. And this happens, there's actually 3 different ways that we think of changing the pressure isothermally. One way is you just pump more of the same mixture into a container, constant volume, that makes the pressure go up. Another way is to take that same volume of gas, you close it and you squeeze the piston, or you put it in a balloon, you squeeze the balloon. And those things will make the volume get smaller, but at constant temperature by ideal gas law, the pressure would go up. Or you could squirt in inert gas, so you add extra argon to make the pressure go up. In this situation, when I look at mole fractions, the mole fractions change in all of those cases. Either when you add inert gas, you're diluting you're adding more total moles. So your numerator is number of moles of this gas, of the special gas, divided by total moles. If I add a whole lot of argon, the total moles gets bigger. So therefore, the mole fractions all go down. Or if you compress it, you actually make a reaction occur in order to maintain this equation to be true. You can, very often it's helpful to talk about a different equilibrium constant, the concentration equilibrium constant, which is the ratio of the concentrations. This one has dimensions of concentrations to some power. Liquid phase, we do this one a lot. Probably did it in high school again. You can write it in terms of the ideal gas law. You can write it as the mole fraction, the partial pressure divided by RT instead of C. That's the same thing for an ideal gas. And you can factor it around, and you end up with a factor like this: the standard state pressure divided by RT to the delta nu. And so that's the relationship between the concentration equilibrium constant with dimensions, Kc, and the dimensionless equilibrium constant, Kq. And you can see this one does not depend on the pressure either, but it does depend on the temperature. So you pick up some funny factors of temperature in this kind of case. Since the Kc didn't change, it's a constant independent pressure, therefore the ratio of the concentrations also didn't change, which typically means that just the concentrations will stay the same. So that happens if you add inert gas to a sample. So I have a low pressure sample in my bowl, I squirt some inert gas in, the total pressure goes up, but the equilibrium of the reacting species doesn't change because their concentrations don't change at equilibrium. However, if I did the same thing where I have my reactive species at equilibrium at some pressure, and I squeeze the piston to make it higher pressure, if there's a change in moles of gas, the concentrations will change in that case. Well, actually, not the easiest way to see it is that the concentration product would have a now factor 1/v to the delta mu. And so the volume changed, then there'll be a change. So now the number of moles of each species would change. The Kc would stay constant with the pressure, but this factor would come in and it would change the number of moles. So a reaction would actually occur. And so either way you look at it, from Kc point of view or KQ point of view, if you do the analysis carefully, you'll see the result you might expect, but maybe not so obvious. So I call this obvious, but I've definitely seen a lot of students not get this right. Now let's think about the obvious pressure effects on kinetics. If the mole fractions are held constant, so no reaction, it's just a whole constant, and I just compress the gas. So I have a composition, and I just closed system, I just squeeze it. Then the concentrations will all go up by that rate because the volume went down. And then I have different situations. If I have a unimolecular reaction and the K of that reaction is independent of the pressure, then the rates will increase because the C increases, the concentration increases. But the total number of moles of stuff that's reacting per second over the full volume will not change, because this is the rates per unit volume. And to get the total number of moles, I have to multiply by the volume, but the volume got smaller by just as much as the concentration went up. So the total rate in terms of moles per second is unchanged for a unimolecular reaction. But for a bimolecular reaction, you have two powers of concentration, the two reactants. And so the rate per unit volume goes up as p squared, and the total moles integrated over the whole volume increases p to the first power. And you can see this is what's going to happen and make the equilibrium change, because if you have an equilibrium between a unimolecular reaction in one direction and bimolecular recombination in the other direction, then one of the rates is going to go up. And the Kc is equal to the ratio of K4 divided by K reverse of the two rate coefficients. Now, adding inert gas at constant volume isothermally increases the pressure, but does not affect the concentrations, doesn't affect the Ks, so it shouldn't cause any effect. So if I just have a bulb of gas, it's doing its own thing. I squirt a little bit of argon in there. It should not do anything. But actually, it does. And that's the thing I want to talk about now. And it's that the rate coefficients, the Ks, are not really rate constants. It's definitely good to call them rate coefficients, because they're not constant. And they depend on more than what the reactants are, what the products are, what the temperature is. They, of course, depend on the solvent. And you guys all know that, kinetic solvent effects. And of course, the solvent changes the equilibria as well, because it changes the thermo of the species. They also depend on having interfaces. So I put a hunk of platinum in there, you can get the changes. If I put this whole thing inside a strong laser beam, you can actually get changes in what happens. That whole phenomenon is not present in RMG, but it would be a good addition. But a very important thing for the kinds of systems that RMG is used for like pyrolysis and combustion systems or atmospheric chemistry, is it depends on the pressure of the gas, and actually also on the gas composition. And there's several different effects. So the big effect that we're going to talk about the most is that if you're at low pressure, the thermalization rate slows down because there's fewer collisions to carry thermal energy around inside the system. And you can get the thermalization to be slower than a reaction. So if you have a fast reaction and you have a slow thermalization, the reaction can force the system to become non-Boltzmann, where the energy distributions of the species involved in that fast reaction no longer conform to the Boltzmann law of populations. That completely screws up all of the rate calculations and the rate. Everything's completely affected because the whole idea of Arrhenius rate law is that the little Boltzmann tail up above the barrier is what's causing the reaction. If the molecules are energized. And the whole formula assumes that that population of that little tail is given by the Boltzmann formula. But if you're in a situation where the reaction is so fast or the thermalization is so slow that you get out of equilibrium, out of thermal equilibrium, so that the energy distribution is no longer Boltzmann, then all the formulas and all our assumptions, and actually the entire Arrhenius law is not right anymore. So this turns out to be quite a big effect in some situations. There's a small effect that some of the very fast reactions in gas phase can be diffusion limited. And when I change the pressure by adding, say, inert gas, I add more collision partners to make the diffusion slower. And so some of the reactions that are really fast, some of the fast bimolecular reactions will be affected by this. Maybe another comment about that is because the Kc does not change with pressure, that means the ratio of the forward to the reverse reaction does not change. So if I have a recombination reaction, two radicals, they very rapidly get together. They might get diffusion limited if I have a high enough back pressure, say argon in the way. If that happens, the Kc is not affected, so therefore the dissociation also must be slowed down by exactly the same amount that the diffusion slowed down the recombination. So this might not be so obvious and intuitive, but it has to be exactly true, otherwise the Kc would have to change. But we know it doesn't. And then finally, at very high pressures, a whole bunch of new things happen. So you then have a non-ideal gas, and it really affects the thermo, and it looks more and more like a solvent if you're really high pressure. So really high pressure, you don't follow the ideal gas law anymore. You get some extra thermoterms, and you also get things called volume of activation effects that the volume of the transition state and the volume of the individual reactants are slightly different. And if you have a gigantic pressure, that P delta V is big enough that you can discern it. But that kind of stuff is usually only seen in diamond anvil experiments or stuff inside geology, like under the center of the Earth, where the pressure is super high, and not really that relevant to us. Usually. All right. The types of reactions that are pressure dependent, where the Ks are pressure dependent, we have kind of two common cases. One is unimolecular reactions in gas phase. Very often there's a pressure dependence, and it's called fall off. You guys know, you hear this fall off? And what it is that you have a rate at all the high pressures, the rate is independent of pressure. But as the pressure gets lower, all of a sudden you see the rate just slows down for the unimolecular reaction. And that's because it's becoming limited by how fast the collisions with the bath gas can heat up the reactant to make it keep on falling apart to products. And you get this characteristic shape where it's for you guys flat at high pressure and then falls off and becomes linear with pressure at extremely low pressures. And there's kind of a curvy region in the middle. Okay. So that's relatively simple. And that was actually proposed theoretically by Lindemann almost exactly 100 years ago. And that's actually, to my knowledge, the first theoretical prediction of a kinetic thing that was actually true. A bigger effect is if you have an exothermic A plus B equals C reaction. So two things, addition reaction or recombination reaction. These reactions are often exothermic because you're creating a chemical bond. When you first do this reaction, all of the exothermicity of the reaction is inside the C molecule that's formed. And that can be a lot of energy. If it's forming a bond, say it's a radical recombination, you might have 100 kcals of energy dumped in a dinky little molecule. And you can divide 100 kcals by the tiny heat capacity of a single molecule. And you can realize that molecule is like effectively really, really hot. And so it needs to be cooled by a lot of collisions with the bath gas to get back into thermal equilibrium. So it's going to be way out of equilibrium initially. And what can happen is if that highly excited C can do anything, it might do it. And so you get a lot of crazy stuff. And this is maybe is the most complicated and also most interesting because it's a big effect. This thing is big, but it's not such a big deal. It's easy to do. Lindemann figured it out 100 years ago. But this one here is pretty complicated. It's still kind of challenging. So the fundamental issue is you need many collisions to add or remove the energy associated with a chemical reaction. And the thermal relaxation or the heat up time will be longer than the chemical reaction time if the pressure is low enough. And then the energy distribution non-Boltzmann, and there's no clear temperature anymore, and the whole thing goes to kablooey, all of our theory. So let's look at how this looks like. So suppose I have A plus B and they react, they form very energized C, but if I have a high back pressure, lots of argon there, then the collisions with argon take away that energy quickly, and I form basically Boltzmann C pretty quick. So this is the normal situation that RMG would correctly model today with what you guys know about. It would know the high pressure limit reaction for A plus B, it gets a K. It says, well, I don't worry about C star, it's not there because it goes zoom right down to C. So I write it A plus B goes to C, I write down Arrhenius rate law, I'm good. All right, and so in this kind of model, I would say, okay, well, the reaction goes C stepwise. A plus B goes to C, and later C has some collision that gets warmed up and has some Boltzmann tail and it gets over the barrier, and then that goes to D. And then much, much later, D gets enough collisions that it might go back, or maybe some of it even goes out and makes an E plus N. And you can see the rates for these later steps are really small compared to this first thing, right? So for this one, basically, there's only 3 rate coefficients. 1, 2, 3. 3 transition states, 3 rate coefficients. It all matches up with like how we have the picture from high school. Everything's cool. However, at low pressure, then we get some extra stuff going on, because what happens is I form C star, the energized C, but the collisions are too slow and they can't take away all this energy. And I'm forming C star faster than I can cool it down. And it's going to happen is I'll build up a pretty good level of steady state concentration of highly energized C. And it's so energized, it's above the barrier to isomerize to D. So it's just going to go whoosh right over to D because it's way above the barrier. And I have a high population of those molecules. And this rate is going to be totally weird because it's not from a Boltzmann tail coming up over this hill. It's from a huge population being dumped in at this energy, just above the energy beta speed. And so it's got some wacko, some really strange rate. And it's going to go over here. And then the D star of this form can do the same thing. Some of it will have collisions and get cooled down and form D. But a lot of it will just go flying over the second barrier. So it looks like, if I look at it experimentally, I see A plus B disappear and instantly E plus F appear. So it looks like I have a reaction. A plus B goes to E plus F. And in fact, there's a lot of cases in literature where that's what people wrote down. A plus B goes to E plus F. That's what we observed. We get a rate law. It looks like it's Arrhenius rate law of A plus B going to E plus F. They don't know anything about C or D even existing because they don't see them. All they see is E plus F. And they publish in the table. But then we look at it and we say, wait, it doesn't match up with any reaction template I ever saw. How the heck did all those bonds rearrange and break and stuff? And actually what happened was it did normal reactions. A plus B is a normal to C is a normal reaction, C to D is a normal reaction, D to E plus F. So it's 3 normal reactions, but all got convolved into one zoom reaction across the top. So then if we increase the pressure, we'll start seeing that these other reactions start to be more important. And so we want to describe this. We actually need 6 Ks for A plus B going to C, A plus B going to E plus F, A plus B going to D, C going to D, C going to E plus F, all 6 of these guys. And so this is like a lot different. And all of these Ks will depend on the pressure. And basically none of them will be arenes. So this is totally weird. Yeah.
So C star and C, they share the same like graph structure.
They're the same molecule. It's just C star is just vibrating like crazy, and C is just sitting there.
And so is there any way that we could like get an energy for C star, or is that just totally unknown?
Yeah, I mean the energy of C star is just slightly above the energy of A plus B mostly. It's a little tiny like Gaussian peak here or something in outer space, and you can calculate what it is. And people have done experiments where you shine another laser that takes C star up to say and ionizes it or something, and you can actually do that.
And but when we're doing like computational quantum chemistry and Gaussian or Orca, we're getting the C and D without the star, just like the lowest energy, clock energy.
Yeah, so quantum chemistry, we usually calculate the stationary points. So we would get the stable structures of A and B, we get the transition state from A plus B to C, and we get the stable structure of C. Now, the quantum chemistry also knows the vibrational frequencies. So you can infer there must be a lot of vibrational energy levels of C in here, and we can estimate them from the quantum chemistry. And up here, there's some of them that happen to have energies about the same as A plus B. And you can even try to calculate how many of them there are up here, and try to get the rate if you're good. You can also do experimentally, you can do it reverse. You can take C and shine a laser on C to jump it up to energy of C star, and then see A plus B appear. And actually, that's experiments I did. That was my PhD. And then you can infer from that rate what the reverse must be. Also with a lot of calculations. All right.
So this it looks like any other collision with other species can cool it down from C star to C.
Yes.
Why is it that oftentimes there are only efficiency coefficients for some species?
Yes. So experimentally, oftentimes people run the experiments where they have one background gas that's the dominant. So they do it in argon or nitrogen, and so the collisions of everything with the argon or the nitrogen just dominate because it's a million times more argon than anything else. Mm-hmm. And then you can measure it. You can measure the same reactions in argon, and you can measure in nitrogen. You get slightly different rates because the cooling is slightly different. Mm-hmm. In the real system, of course, you have a real mixture, but people haven't measured every single mixture. Mm-hmm. Similarly, for the calculations, you can calculate the cooling rate by the collisional rate. But again, the calculations are kind of expensive, and so people have only done it with a single collision partner at a time. Right? However, there's papers by Burke, who's a professor at Columbia, and he did a lot of like, you had a mixture of two gases. So like air, nitrogen and oxygen. How would that change the story? And in some weird situations, it actually changed the story a lot. And he has a bunch of papers about that. I say commonly it doesn't do much, but there's some situations. Actually, steam, H2O, turns out to be a really strong collision partner for a lot of things. And it's really good at taking off energy. And so a little tiny bit of steam can actually completely screw up the kinetics. And that's known experimentally from combustion stuff. And also, I have perfectly calculations. All right. Now, how would you calculate such a thing? The way you do it is you say, okay, forget Boltzmann. I don't know any temperature. I just have to do E's. And so I'll just do an energy balance and kinetics for each individual energy state. So do population balance equations for each energy state separately. They're all coupled together. So I have to do them all together, and I get some gigantic matrix of equations called the master equations. But it turns out it's linear in the populations of each species. So you have like a big linear algebra problem. It's a complicated one, but it's well studied, and there's textbooks that show you what the equations are. And that's the master equations. And the parameters that show up in this, very importantly, is K of E, called the microcanonical rate coefficient. And it's instead of K of T, it's how K depends on the energy of the states. And you get a different rate for every different energy state. The higher ones react faster, and the low ones react much slower. And you can compute this thing actually quantum mechanically. It's not hard to compute it. A little bit harder to compute is the collisional energy transfer, of how fast the C star gets pulled down to C. And you can calculate that, but it means you have to consider all of the angles at which the argon could smash into your molecules. And so people have done that, and particularly a guy named Aaron Jasper, is famous for figuring out how to do those calculations. And so you can read his papers and learn how to do it. So it's possible to get these omegas. You can also measure them. The measurements are also super tricky, but people have figured out how to do it. A person named Amy Mullen in Maryland right now is like the world's expert on that thing, and some other people have done it. You also need a thing called the density of states, rho of E. Rho of E is the microcanonical analog of the partition function that shows up in thermo. So in Boltzmann canonical thermo, you get this thing Q of T. You guys have probably dealt with that. Rho of E is the analog. It's like how many quantum states are there in each little band of energy? And so it sort of affects the equilibria. So if you have like an equilibrium between energy level here and energy level here, the ratio of the Ka divided by the Kd would be related to that the rho of A plus B times Ka is equal to the rho of C times Kd. And so it's like the analog of a micro, you get what's called detailed balance. And RMG estimates all these numbers for you. Of course, they're estimates. They might not be right. But at least you get a number. And it's good. You can compute these things from quantum chemistry. And Arcane can do it for you. And Arcane can mix up. If you have some of these from quantum chemistry and some of them from RMG's estimates, you can just mix them up to get the full simulation. All right, here's something about the equations. This is the relationship between the canonical partition function and the density of states, rho of E. And here's the one for the rate constants. This thing that we always use in RMG is called the high pressure limit rate coefficient. It's the one that doesn't, where you're in the limit where you have such high pressure that the thermalization is fast. So you can use Boltzmann assumption and you get K of T. You add this little infinity to warn people that it's only good at high pressures. And this is the formula for how it's related to these other guys. And there's the K of E. So this is the, what do you call this, Laplace transform from K of E to K of T. And you can get the inverse Laplace transform to go from K and Q back to rho and K. And that's how RMG goes. The master equation solution you get from all those complicated balance equations only gives you the time dependence of the populations of every energy state. It does not give you a rate coefficient. This is super annoying. So you end up with thousands and thousands of these P of T's, of all the energy states, and you have to somehow convert them back into a small number of rate coefficients to put into your Chemkin model or your RMS model. And there's a lot of ways to do this, and there's a whole complicated literature about it. Basically, in RMG, we recommend you use the most stupid way of doing it, which is called MSE, the Modified Strong Collision Approximation. And it's because we recommend it because it's really robust. So you always get something that's not too much nuts, but you never get the right answer because it's pretty gross approximation, but it's usually within 1 order of magnitude of the real value. The accurate method is a thing called CSE. However, usually it's good, but when it fails really bad. Like it doesn't even give you any number at all. That really breaks RMG. Or it gives you numbers that are completely nuts. It might give you negative rate constants. It's very annoying. So if you want to learn about this, the good version of CSE is a very nice paper by Georgievsky, 2013. The Allen paper from this group explains the difference between these guys and some comparisons. And then this last year, there's a parity discussion, and I was there. And this is one of the topics discussed. I just submitted another paper about this topic, about trying to figure out like what the errors are and how to fix this, and it's like an ongoing challenge. All right, now let's talk not about numbers. That was parameter error. Let's talk about truncation error. So this is a challenge for RMG because the well skipping introduces those extra reactions. Remember I said that we only had 3 reactions to start with if we did RMG, but in fact, now I need 6 rate coefficients. So I need to have 6 extra reactions appearing in my list. three extra reactants, and I need rate coefficients for it. And RMG needs to know they even exist. So if you do RMG the way you guys have learned it so far, all you would get was A plus B reacts to C. Boom, all done. And then if C accumulates to a high concentration, you would say, okay, and C goes to D. And then if D accumulates to a lot of high concentration and you're running at a high enough temperature, maybe you also get D goes to D plus F. So you get those three, that would be it. But in reality, I want to get this one because that's actually the main reaction of low pressure. A plus B goes to E plus F. So I need to change how RMG is going to construct the reaction network. And this is very similar to the species selection problem that we discussed earlier, but now it's trickier because before when we did this species selection, you have a core and an edge, and you only have a single step from the core to the edge. Now you have a core and you have a super duper jump that leaps way deep past the edge all the way far away and make some funny product. So you have to track that down, or that whole pathway. And the way it does it is first it knows the reactions it does know how to do. This is core to edge. And it says, okay, now I'm not going directly to C, I'm actually going to form C star. So it adds a C star into the model. And then it says, oh, if C star accumulates, then C star might make D. So now I have like a growing network through these pseudo-species, C stars, these highly energized species. If you want to get a better explanation, I have to read the documentation online, but I'll keep going. You need to have an edge flux to test. And so we need to estimate the rate of formation of this species from the A jump through C star gets to D reaction. Actually, it gets through C star and D star to get to D. And I need to have some K, but I can't compute K because I don't have the whole network yet, so I can't form the population balance equations properly to get it. So instead I try to build an overestimate of K. And the idea of an overestimate is that if this is still a small number, then I feel safe to completely ignore it. And I can cross this reaction out and I don't have to worry about it. So then there's a whole rigmarole about how the heck I'm going to construct an overestimate of a rate coefficient that I can't actually compute yet. But we figured out a way to do it. And so you get the overestimate, and from that, you like solve this little mini problem, ignoring the fact that E plus F might exist. And that gives you kind of an overestimate of how much D star you'd have because it's not being depleted by being lost E plus F. And if then the D star is forming E plus F, then you know you better put it in. That's the general idea. And well, anyway, if you really want to do this, you have to read the papers. In the end, you'll now have three different kinds of reactions for A plus B. A plus B goes to E plus F. And you'll see all three of these in models if you look at them. So one of them is people assume you're in the high pressure limit. A plus B goes to E plus F. They assume it's near Arrhenius. And the rate law would be a K infinity of T times the const A times const B. And this is the one you're all familiar with. Then as you lower the pressure, you have to change it. And now you put these funny symbols, this plus M with parentheses around it. And you've probably seen some mechanisms that have this. This is warning you that now the K expression has to depend on the pressure. It still has the rate law that it depends on the concentration of A and B only, but the M is kind of implicitly in there because it's showing up in the pressure. There's several different forms of what this K are in literature, and the two that I like are Troa's form, which is excellent for unimolecular reactions, and the Chebyshev form, which is more general. Unfortunately, somebody in the past invented another form called log P, and log P doesn't fit very well, and it has a lot of potential screw-ups. But you'll see a lot of mechanisms use it anyway. I'm sorry. So you may have to deal with this. I hope you don't have to. I hope you can just use Troa and Chebyshev. Part of this was a stupid software problem that the free version of Chemkin had log P but not Chebyshev. So all the cheapo university groups were using the free version, and they all used the stupid log P thing, but it then didn't fit. So then the literature was like a total mess because their Ks didn't make any sense. But anyway, there's a lot of mechanisms around from that time period before people had enough money to buy a commercial version. and before they invented Cantera. And then finally, at very low pressure, so if you're doing things in vacuum or in interstellar space, then you'll get these reactions where you write them as termomolecular, A plus B plus M. And the rate law now has 3 concentrations in it, and the K is depicted as K0 to warn you that it's the extreme low pressure limit, near zero pressure. And the concentration of M is the pressure by RT approximately. And so you can see this is just linear pressure dependence at the end. In here, you get goofball curvy, nonlinear pressure dependence. So when do you have to bother with this? When the pressure is high and the temperature is low, what I call normal chemistry, you usually don't have to worry about it, only for some specialized reactions. So 1 atmosphere, if you're below 800 Kelvin, you can pretty much ignore the fact that pressure dependence exists, and you'll be wrong in a couple specialized reactions, but most of the time you'll be fine. On the other hand, if you're modeling a lab experiment, so for example, Shine Deep does some experiments at like 10 Tour, so that's somewhere down here, and maybe around 1,000 or 800 Kelvin. He is in the region of the pressure dependent limit. So almost all reactions at his condition will be pressure dependent. So you go pretty quickly from having nothing being pressure dependent to everything being pressure dependent, just by raising the temperature a little bit or by dropping the pressure by a couple orders of magnitude. Now, problem for you is that the laboratory people, the experimentalists, invented methods that are great at low pressure for measuring things. So almost all the experimental data you'll find is like down here. And however, the engineers who build stuff, they all work at like 1 atmosphere or above, because nobody wants to bother with vacuum stuff. So we're all like in here somewhere. And so now we have the problem that all our experimental data is at some condition where all the rate laws are completely different than the rate laws that we actually should be using. So you can imagine this has caused some problem in literature. Anyway, it's easy if you have your reaction, you know a little bit about it. It's easy to, there's some rules of thumb about telling you whether you need to worry about it. Pressure dependence or not. You can read this paper about it. All right. RMG does the pressure dependence automatically as you build a full kinetic model. So if you click pressure dependence on as one of the inputs, it'll automatically consider all this pressure dependence stuff everywhere. Be warned, it's going to make the whole calculation a lot slower to build a model because it has to consider all those energized intermediates and all the possible isomerizations and dissociations and everything that you could possibly do before it can even finish one reaction. But it'll do it for you. So if you have a nice supercomputer account, you start it up, you go away and come back in 3 days, you probably have a mechanism. But this whole thing, the only way it's possible to do this is it's using the roughest approximations. It's estimating everything because it's computing tens of thousands of these Ks of T and P that are really complicated calculations. So it's just not realistic that you're going to get everything perfect doing this like that. Now, that's for the engineers, this is fine. They don't really care. They just want a model. It's semi-good. All right. For the physical chemists, they really care. They want every single rate coefficient to be, God's truth. This is the what I can certify. I can publish it in the Journal of Chemical Physical Reference Data that this is the true number. So they really care. So they're not going to do the RMG way. So they want to go and do nice fancy quantum calculations, get whatever experimental data you can get. Then you're going to fiddle around with all the inputs and the tolerances and the methods and make sure you have the certified great one. And when you submit it to the referees of Journal of Physical Chemistry, they're going to say, oh, that's brilliant. And you get to publish your number. All right? And that's when you want to use Arcane. So Arcane has a lot of software that's completely overlapping with what's in RMG. But the use case that's envisioned is completely different. So the RMG use case is envisioned that the human is doing nothing except pressing go and just letting the computer chug away to give a model for you. And the arcane one is basically the human is doing almost everything, and the computer's just to help you a little bit. Okay, so there's the two limiting cases. So you have to decide which case you're in. And we've talked about trying to do like something in the middle, where you might do some sort of semi-arcane something or other to try to soup things up. But I would say, I don't know, it's not really working right now anyway. It's a possible thing you might want to do. But right now, that's not the way it is. So you either can do the RMG, estimate everything, don't worry about the accuracy too much, or arcane, worry about the accuracy, but expect to spend 3 months on one reaction. And there's some recent papers by Lon and by Matt Johnson that give a lot of details about this arcane stuff, and it has a lot of nice features. It's actually really nice software, but it's really for that specialized situation. And just to end with a little history of this, the pressure-dependent construction algorithm was invented by David Matthew, who was my first PhD student. And at that time, he implemented into a software who, unfortunately, Exxon owned the copyright. They would not allow it to become public. So we were able to publish results using it, and to publish paper and publish the algorithm. But then we decided to switch, and actually this is part of the impetus why we created RMG in the first place. So it was to have an open source version. And then, but when the other student, Jing Song, wrote RMG, she didn't understand this PDF thing, it was brand new. And she said, forget it, I have enough headaches, just getting RMG to work. So she just did normal high pressure limit rate constants. And so the original version of RMG that was available up until about 2011 didn't have any pressure dependence. Then Joshua Allen in 2011, 2012 implemented basically variations on David Matthews' algorithm, slightly improved, and actually implemented a bunch of other methods to compare them with, and wrote the software really nicely. And he also he did it in both RMG Java and also in the new RMG Pi that he was developing at the same time. He was quite good software developer. And then recently, Matt Johnson and Alon Denberg have added a bunch of improvements, broke out Arcane as a clear, separate software that it's kind of more usable than it was before. And this paper about how to refine pressure-dependent networks to get better numbers, you might be interested in. All right, and then I'll just post a lot of slides with a lot of details about how RMG does things, but it's more than I can explain. Questions?